Welcome, curious minds, to The Deep Dive. Today we're plunging headfirst into a topic that, honestly, sounds like the wildest science fiction.
It really does.
Yet it's rapidly becoming our tangible reality.
Uh-huh.
So imagine this, if you will. There's a computational problem, right? So vast, so incredibly intricate, that even our fastest, most powerful classical supercomputers, the ones that fill rooms, they'd be stuck grinding away at it for, get this, an astonishing 10,000 years.
10,000 years. It's almost impossible to conceive.
Right. Now, what if I told you that a quantum computer, this new kind of machine tapping into the weird rules of reality, it tackled that exact same problem
And
spat out the answer in a mere 200 seconds.
wow, 200 seconds versus 10,000 years.
Not a typo. 200 seconds. It's a truly monumental shift in how we conceive of computation and, frankly, what's even possible. Okay, let's unpack this.
That is the perfect place to start. That feat by Google's Sycamore quantum computer back in 2019, it really threw down the gauntlet.
Yeah, it definitely made headlines.
And it leads us straight into our source for today's deep dive. Michio Kaku's 2023 book, Quantum Supremacy: How the Quantum Computer Revolution Will Change Everything.
Kaku, right? He's the theoretical physicist, the one who's really good at explaining complex stuff.
Exactly. He's a renowned physicist and, fantastic science communicator. And in this book, he takes on the really ambitious task of demystifying these incredibly abstract, often, let's face it, bewildering ideas for everyone.
And what's his main argument, his big idea?
His central thesis, the core argument he lays out, it's pretty stark, actually, and very thought-provoking. He basically posits that we are reaching the practical end of the silicon-based digital age as we know it.
The end of silicon. Like, Moore's Law is over.
Pretty much hitting its limit, yeah. The book itself, it's about 350 pages, structured into 4 main parts, plus an intro and epilogue. It's designed as a comprehensive but still really engaging guide through this whole new field.
Okay, so our mission today, for you listening, is to cut through all the noise, the intense hype that always surrounds these big new technologies.
There's definitely a lot of hype.
And all the bewildering jargon, frankly.
Yeah.
We want to give you a comprehensive but still engaging understanding of quantum computing's immense promise and its very real, very tangible challenges.
It's not all smooth sailing.
Not at all. Think of this as your shortcut, maybe, to being genuinely well-informed on a topic that truly could reshape our future. I mean, from the smallest molecular stuff that governs life all the way up to the biggest questions about the universe.
It really spans that whole spectrum.
So we're going to explore what makes it tick, where it came from, the big moments, the breakthroughs, and crucially, what it might mean for all of us. So let's begin with the real basics, that foundational difference that sets this new era apart. You're undoubtedly familiar with how our current digital world works, right?
Yeah, phones, laptops, the internet.
Everything. Your smartphone, global banking, social media. Yeah. It all runs on something called a classical bit.
The good old bit. 0 or 1.
Exactly. A fundamental unit of information that exists in one of two distinct states. It's either a 0 or 1, like an electrical switch, basically, off or on.
Simple, binary.
Our computers process, zillions of these zeros and ones sequentially, one after the other, at incredible speeds. It's the bedrock of our entire digital infrastructure.
Yeah.
It's amazing, really, a testament to human ingenuity.
Absolutely. Decades of refinement.
But now we're talking about something entirely different. So what could possibly come next? What's beyond just making those zeros and ones faster and smaller?
Well, what comes next is the quantum bit, or qubit, as it's usually called.
Qubit? Okay.
And it's much more than just a faster, smaller version of a classical bit. It's a fundamental paradigm shift. It completely redefines how computation even works.
Oh, so?
Unlike that classical bit, which has to be either a 0 or a 1, definitively. A qubit harnesses the strange rules of quantum mechanics.
The weirdness.
The weirdness, exactly. Which means it can exist as a 0 or a 1, or, and this is the crucial kind of mind-bending part, it can be both simultaneously.
Both at the same time.
At the very same time. This inherent ability, totally unique to the quantum realm, allows for a form of what's called exponential parallelism.
Okay, exponential parallel. Let's break that down.
Okay. Imagine you're trying to find your way through an incredibly complex maze, like millions of paths.
Right.
A classical computer would basically try one path systematically. If it hits a dead end, it backtracks, tries another, then another, one at a time.
Okay, methodical but potentially slow.
Very slow for complex mazes. A quantum computer, though, by leveraging the power of multiple qubits working together in this quantum way, could theoretically explore all possible paths through that maze at the exact same moment.
All at once.
All at once. It's not just faster processing, it's
Okay.
a fundamentally different way of tackling the problem.
Wow. Okay, so that's the qubit.
Yeah.
But you mentioned the weird rules. This is where it gets really interesting, right?
Oh, yeah. This is where our everyday intuition just kind of breaks down. The first big concept is superposition.
Superposition.
Think of it like, okay, a coin spinning in the air.
Okay.
While it's up there, twirling, you can't definitively say it's heads or tails, right? It's in this uncertain state, simultaneously both, in a way, until it lands and you look at it.
Right. Then it's definitely one or the other.
Exactly. Qubits operate in a profoundly similar way. They exist in this superposition of multiple states at once until you measure them. Then they collapse into a definite 0 or 1.
But before you measure, they're both.
Effectively, yes. And the computational power this unleashes is, well, it's truly mind-boggling. Kaku emphasizes this point brilliantly in the book.
How much power are we talking?
Get this. With just n qubits, you can compute 2 to the power of n possibilities simultaneously.
2 to the n. Okay, that grows fast.
Incredibly fast. To put that into perspective, Kaku points out that just 300 qubits, assuming you could perfectly control them, which is a huge if right now.
Right, the control problem.
But just 300 qubits could represent more possible states than there are atoms in the entire observable universe.
Wait, what? More states than atoms.
More states than atoms. It's not just an incremental speed up. It's an astronomical exponential leap in processing capability.
So each new qubit doesn't just add power, it multiplies it.
Exactly. It doubles the computational space you can explore. 2 qubits explore 4 states, 3 explore 8, 4 explore 16, 300 explore 2 to the 300. A number so vast, it's meaningless to try and write out.
Okay. My brain hurts a little. Superposition. Got it. Kinda. What's the other weird rule?
The other really bizarre but equally crucial concept is entanglement.
Entanglement. Okay.
What's truly fascinating here is how 2 or more quantum particles, like qubits, can become intrinsically linked, so deeply connected that the state of one instantaneously influences the others.
Instantaneously.
Yeah, no matter how vast the distance separating them. Across the room, across the planet, across the galaxy, theoretically.
Okay, now that does sound like science fiction. How is that possible? Is that by like a speed of light?
That's exactly what troubled Einstein. He famously scoffed at it, calling it spooky action at a distance.
Spooky action.
I like that.
Because it seemed to imply information traveling faster than light, which violates classical physics, violates relativity. But here's the thing. Experiments have repeatedly verified it's real.
So Einstein was wrong about that bit.
Yeah, his intuition flagged it as deeply weird, but quantum mechanics, as described, holds up. There's something called Bell's theorem.
Bell's theorem?
Yeah, John Stuart Bell, a physicist. He basically came up with a mathematical proof in the 60s. It demonstrates that the correlations you see with entangled particles cannot be explained by any classical, local, hidden variables. Meaning, basically, it mathematically proves this spooky action isn't just some trick or missing information we don't know about. It's a real, fundamentally non-classical feature of the universe. The connection is real and instantaneous.
Wow. Okay, so what's the significance of entanglement? What can you do with it?
Its significance is profound. It's not just a weird quirk. It's the fundamental basis for things like quantum teleportation of information.
Teleportation. Like Star Trek.
Huh. Well, not quite beaming people around. Importantly, it's teleporting the quantum state, the information, not the matter itself, but still incredibly powerful.
Okay. Information teleportation. What else?
It's also key for highly secure communication protocols like quantum key distribution or QKD. Yeah, using entangled particles to generate encryption keys that are theoretically impossible to eavesdrop on without disturbing the system and alerting the users. Could lead to truly unhackable networks. We'll definitely talk more about that later.
Unhackable. That's a big deal.
Huge. And Kaku, in his book, uses some great illustrations to help make these abstract ideas more graspable. He talks about the double slit experiment.
Ah, the famous one with particles going through slits.
That's the one. It beautifully shows wave-particle duality, how tiny particles can act like discrete points and spread out waves depending on whether you're watching them. It really messes with our classical view of things.
Yeah, observation changing reality.
Exactly. And he also brings up Schrodinger's cat.
The cat in the box. Is it alive or dead?
Right. Now, that's just a thought experiment. Obviously, no cats were harmed. But it vividly portrays that idea of superposition, the cat being both alive and dead until the box is opened, and it's observed bringing that weird quantum state into a more relatable, macroscopic, though still deeply weird picture.
It definitely makes you think.
And it really does spark these profound philosophical debates, like the Copenhagen interpretation, the idea that reality kind of chooses a state only when we measure it. Versus Hugh Everett's many worlds theory, which is even wilder. It suggests that every possible outcome of a quantum measurement actually happens, just in separate, parallel universes that branch off.
Many worlds. So in another universe, the cat is dead, and in another, it's alive.
That's the idea. And the implication Kaku touches on, if quantum computers eventually let us simulate things well enough to explore or maybe even confirm aspects of many worlds, it would fundamentally challenge our understanding of free will, cause and effect, the very nature of reality. These aren't just tools. They could be keys to unlocking really deep existential questions.
Okay, that's a lot to take in. Superposition, entanglement, many worlds. It really makes you appreciate how far we've come in figuring this stuff out. But where did this journey, this story of computing, even begin? It wasn't just with silicon chips, right?
Oh, not at all. It's incredible to reflect on. To truly appreciate this quantum leap, you really need to see it as maybe not inevitable, but a logical next step in a long, fascinating history.
Take us back. Where does it start?
Well, you could argue the story of computation stretches back millennia. Humanity's always wanted to quantify, predict, model things. We can start way back, almost 2,000 years ago, not with silicon, but with bronze. Yeah, imagine the Antikythera mechanism, found in an ancient Greek shipwreck in 1901. It's this fantastically intricate device, a complex system of bronze gears.
What did it do?
It was built to simulate the motions of the sun, moon, and planets, predict eclipses. Basically an analog computer for astronomy. It showed an incredibly sophisticated grasp of mechanics and computation, way ahead of its time. An early ambition to model the cosmos.
Amazing. Okay, jump forward a bit.
Let's jump to the 19th century. We meet these visionaries whose ideas, though they couldn't fully build them then, laid the theoretical groundwork. Think Charles Babbage.
The analytical engine guy.
Exactly. He conceived of this mechanical, general-purpose computer, programmable. A revolutionary concept way beyond just calculation.
But it never got built, right?
Not in his lifetime, no. But, crucially, working alongside him was Ada Lovelace.
Lord Byron's daughter, the mathematician.
That's her. And she wasn't just a mathematician. She wrote what's widely considered the very first algorithm specifically designed for Babbage's hypothetical machine. She saw its potential went far beyond just crunching numbers.
The first programmer.
Essentially, yes. She recognized the machine could process any kind of information. Symbols, logic, not just numbers. That conceptual leap that computation could be about more than arithmetic was profound.
Okay, so Babbage and Lovelace set the stage conceptually. Then came the 20th century.
And that's when the foundations of modern electronic computing were truly laid. You have the brilliant Alan Turing.
Codebreaker, computing pioneer.
Absolutely. He gave us the conceptual universal machine, a theoretical model showing any computation could be done by a simple device following rules. His work was utterly crucial in cracking the German Enigma code during World War II.
Which changed the course of the war.
Undeniably. And his theoretical framework quickly led to practical machines like ENIAC in the 1940s, one of the first electronic general-purpose computers. Room-sized behemoths.
The dawn of the digital age.
Right. And then, almost happening in parallel at the turn of the 20th century, quantum theory itself was being born, a revolution in physics.
Planck, Einstein.
Exactly. Max Planck introducing quanta in 1900. Energy isn't smooth, it comes in packets. Albert Einstein explaining the photoelectric effect, showing light acting as particles. Niels Bohr developing his model of the atom with electrons in specific energy levels. These discoveries totally reshaped how we understood matter and energy at the tiniest scales.
So the seeds of quantum computing were planted then.
The seeds of quantum mechanics were. The idea of quantum computing took much longer to germinate. It really got going with Richard Feynman's 1982 proposal.
What did Feynman say?
He famously declared, and you can almost hear his voice, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical."
Love it.
He realized, to truly understand the quantum world, you couldn't just approximate it with classical computers. You needed a quantum computer.
Build a quantum system to simulate a quantum system. Makes sense.
Right. And then David Deutsch in 1985 formalized this, conceptualizing a quantum Turing machine, mathematically proving such a device was possible.
Okay, so the theory was solidifying. When did the killer apps, the algorithms, appear?
That was the next big wave. Peter Shor's 1994 factoring algorithm was a bombshell.
Why? What did it do?
It showed that a quantum computer could efficiently factor large numbers into their primes. That specific task is incredibly hard for classical computers, and it's the basis for most modern encryption, like RSA.
So Shor's algorithm meant quantum computers could break modern codes.
Potentially, yes. It sent massive shockwaves through the cryptography world, a huge alarm bell for digital security. We'll definitely circle back to that.
Okay. And any others?
Shortly after, Lovegrover came up with an algorithm offering a quantum speedup for searching unsorted databases. Less dramatic than Shor's, maybe, but still showed quantum advantage for important problems.
So theory, algorithms. When did we actually start building these things?
The early 21st century saw the first baby steps, the early prototypes, moving from equations on paper to real, tangible, albeit very basic, machines. IBM built a tiny 5-qubit machine in 2001, just enough to demonstrate Shor's algorithm on a trivially small number.
Proof of concept.
Exactly. Companies like D-Wave started building quantum annealers, which are a bit different, specialized for optimization problems. And then others, like Rigetti, began offering cloud access to their small quantum systems, letting researchers experiment.
So it's been this long, winding road. Ancient gears, 19th century visionaries, 20th century physics and code breaking, then these specific algorithms and early machines.
Leading us right up to the much more sophisticated, powerful, and still incredibly challenging quantum systems we're grappling with today. It's quite a story.
Okay, so that brings us more or less to the present. And for the better part of, 6 decades, we've lived by this pretty reliable rule in computing, Moore's Law.
Gordon Moore, 1965, yeah.
It's that familiar trajectory, right? The number of transistors you can cram onto a chip roughly doubling every 18 months or so, leading to consistently smaller, faster, cheaper electronics. It's basically driven our entire digital revolution.
Absolutely. Exponential growth year after year.
But Kaku argues in his book, quite forcefully, that this incredible run, it's finally coming to an end.
He does, and he makes it incredibly clear why. Moore's Law is hitting immutable physical limits. It's not just an economic slowdown, it's physics.
Physics getting in the way. How?
As those transistors shrink down to, well, roughly 5 nanometers now, which is where our most advanced silicon chips are currently hovering.
Tiny. Absolutely minuscule.
Right. At that scale, we slam right into the fundamental weirdness of quantum mechanics itself. Specifically, electrons start to do something called quantum tunnel.
Quantum tunnel, like digging through a wall.
Kind of. Imagine trying to keep water in a leaky bucket, but the leaks aren't actual holes. It's more like the electrons, because of their quantum wave nature, have a probability of just appearing on the other side of the barrier that's supposed to contain them.
So they just leak out.
Effectively, yes.
Yeah.
They tunnel through. This causes errors in the computation, interferes with the chip reliability, and generates a ton of excess heat. Further miniaturization using traditional silicon becomes incredibly difficult, maybe even impossible.
And that's Kaku's central point.
That's his core argument, remember. We are truly at the end of the silicon-based digital age. The party's winding down for classical scaling.
And the implication isn't just, oh, our phones won't get faster quite as quickly.
Not at all. It's much more profound. Without a new computational paradigm like quantum, Kaku argues that progress in fields utterly reliant on massive computing power, think advanced AI, big data analytics, drug discovery, material science.
All the really cutting-edge stuff.
Exactly. All that progress could inevitably stall. We'd hit a computational wall. And that's a future Kaku believes quantum computing can help us avoid.
Okay, so classical computers are hitting this quantum wall. But quantum computers are rising. What does this mean right now? You mentioned the Google demonstration. Quantum supremacy.
Yes. That term, quantum supremacy, generates a lot of buzz, sometimes controversy, but its technical meaning is actually quite precise and really important to grasp.
So what does it actually mean? Is it like quantum computers are just better at everything now?
Not necessarily better at everything. Not yet, anyway. Quantum supremacy, as rigorously defined by physicists like John Preskill, who coined the term, signifies a very specific achievement.
Okay.
It means a quantum machine has successfully solved a particular computational problem that even the world's fastest, most powerful classical supercomputer cannot solve in any reasonable time frame.
So it's about one specific task proving a quantum advantage exists.
Exactly. It's not about general superiority across the board, but a clear, irrefutable demonstration of quantum advantage on at least one carefully chosen problem. It's crossing a threshold.
And Kaku highlights the milestones that show we've crossed it.
He does. The most famous one, the one that really grabbed the headlines, was Google's Sycamore in 2019.
That was the 200 seconds versus 10,000 years one.
That's the one. Sycamore, with its 53 working qubits, solved this highly specific, kind of esoteric problem called random circuit sampling, basically verifying the output of a quantum random number generator.
A task designed to be hard for normal computers.
Precisely. It's designed so the complexity scales exponentially for classical computers. Google's team estimated that Summit, the world's fastest supercomputer at the time, would have needed about 10,000 years to do the exact same calculations Sycamore did in 200 seconds.
That's a staggering difference.
It was a pivotal moment. It really signaled that demonstrable quantum advantage wasn't just theoretical anymore. It was experimentally real, even if the problem itself wasn't immediately useful in a practical sense.
It proved the potential was real.
Exactly. And then, not long after, in 2020, researchers in China announced their own breakthrough with the Juzang quantum computer.
Juzang, how was that different?
It used a completely different approach. Instead of superconducting circuits like Google, Juzang used photons, particles of light, as its qubits. 76 of them.
Light-based quantum computing.
Right. And it performed a different task called Gaussian boson sampling. Again, a highly specialized calculation, this time about how photons behave, chosen specifically because it's known to be exponentially harder for classical computers.
And how to do?
They reported it performed the task something like 100 trillion times faster than the fastest classical supercomputer could simulate it.
100 trillion.
Yeah, so you had these two major demonstrations back to back using different technologies, superconducting qubits and photons, both achieving this quantum supremacy milestone on different problems. It showed the field was advancing rapidly on multiple fronts.
And the progress hasn't stopped there.
Not at all. IBM, another huge player, has been consistently pushing the boundaries. They unveiled their Eagle processor with 127 qubits, then Osprey with 433 qubits.
The qubit counts keep climbing.
They do. Each announcement pushes the state of the art in terms of scale and, crucially, improving the quality and coherence of those qubits as well. It's not just about quantity.
So these milestones solidify it.
Mhm.
Quantum computers aren't just lab curiosities anymore.
They're real, they're rapidly advancing, and they've demonstrably crossed a significant performance threshold compared to classical machines, at least for certain tasks. The dawn of quantum supremacy is here.
And these breakthroughs, they haven't just sparked scientific excitement, right? They've ignited this intense global competition. You called it a new space race.
That's a very apt analogy. It feels like that. The stakes are incredibly high, both geopolitically and commercially. Governments around the world instantly recognize the strategic importance of leading in quantum tech.
So who are the big players? What are they investing?
Well, in the United States, the government passed the National Quantum Initiative Act back in 2018. That allocated about $1.2 billion to coordinate and boost quantum R&D across different agencies, labs, universities, a significant federal commitment.
Okay, $1.2 billion. How does that compare globally?
Well, China has signaled even greater ambition, arguably. They've announced a massive commitment. Reports vary, but often cited around $10 billion towards quantum research.
$10 billion. That's a huge difference.
It's a massive investment. It includes building a dedicated national laboratory for quantum information sciences. And a key part of their strategy, something tangible they've already deployed, is the Michio satellite.
Michio, what does that do?
It's specifically designed for quantum key distribution, that QKD we mentioned, using entanglement to send encryption keys securely between the satellite and ground stations.
Unhackable communication from space.
That's the goal. For national security, having communication links that are immune to eavesdropping, even from future quantum computers, is a massive strategic advantage. It shows China is taking concrete steps towards quantum-secure infrastructure.
Okay, so U.S. and China are major government players. What about companies?
Oh, the commercial race is just as fierce, maybe even more complex. You've got all the tech giants heavily involved, IBM, Google, Microsoft, Intel, plus specialized players like Honeywell, now part of Quantinuum, and startups like Sequantum.
All throwing money at it.
Billions. They're pouring resources into research, development, hiring top talent. Each is exploring slightly different quantum architectures, different strategies, but many have set these really ambitious goals, like aiming for fault-tolerant million qubit machines by, maybe 2030.
A million qubits. We're at hundreds now. That's a huge leap.
It is. It highlights the scale of the ambition and the competition. This race isn't just about bragging rights for the first big machine. It's about who establishes the foundational tech, the patents, the standards, who controls what could be the next dominant computing paradigm.
The nation or company that really cracks this could gain an unbelievable edge.
Exactly. An unparalleled advantage in science, economics, intelligence, defense. It could literally rewrite the rules of global power and information. The stakes are enormous.
Okay, so the potential is clearly immense. The race is on. But despite all this amazing progress, we need to pump the brakes a little, right?
Yeah.
You said these things are fragile.
Extremely fragile. That's the catch. It's crucial to understand that quantum computers are, notoriously delicate. They're absolutely nothing like the robust laptops or even the classical supercomputers we're used to.
And this fragility,
Yeah.
it's the biggest roadblock right now.
It's arguably the single biggest, most fundamental hurdle to building large-scale, practical, fault-tolerant quantum computers. Kaku details this primary challenge as the problem of decoherence.
Decoherence. Sounds technical. What is it, simply?
It's basically noise, environmental interference. Think about even the tiniest fluctuations in temperature, the slightest physical vibrations, stray electromagnetic fields from, wiring or other equipment.
Background noise.
Exactly. Any of that stuff can interact with the qubits and cause them to lose their delicate quantum state, their superposition, their entanglement. It forces them to decohere back into behaving like boring old classical bits, a 0 or a 1.
So the quantum magic just disappears.
Oof, gone. It's like trying to keep a soap bubble perfectly intact in the middle of a hurricane. The quantum state is incredibly sensitive to its surroundings.
So how on earth do they protect these qubits from decoherence?
Well, the main strategy right now involves extreme isolation and control. That means building these incredibly complex, multi-layered refrigerators, are called dilution refrigerators.
The big chandelier-looking things.
That's them. They cool the quantum chips down to temperatures near absolute 0. We're talking just tens of millikelvins, that's thousandths of a degree, above negative 273 Celsius, or negative 460 Fahrenheit. Colder than deep space.
Colder than space.
Yeah.
Just to run a computer.
Just to try and keep those qubits stable for long enough to do something useful. And even then, even inside these ultra-cold, shielded environments, they can typically only maintain coherence, keep that quantum state alive for, microseconds or maybe milliseconds.
Microseconds, that's not very long.
It's an incredibly short window to perform complex calculations. You need to do potentially millions or billions of operations before decoherence wipes out your computation. That's a massive challenge.
Are there any ideas for doing this without the crazy refrigerators?
There are long-term hopes. Kaku points towards nature for inspiration. For example, he mentions how photosynthesis in plants seems to use quantum coherence effects quite efficiently, and it does it at room temperature.
Plants are doing quantum stuff.
It seems so. So maybe there are biological tricks or new materials we could discover or design that are inherently more robust. Another really big hope, though it's still very much in the research phase, is topological qubits.
Topological. What does that mean?
Instead of storing the quantum information in a really fragile property like the spin of an electron, topological qubits aim to encode it in the shape or topology of the quantum system using exotic particles called anyons.
Okay, shape. How does that help?
Imagine information encoded in a knot tied in a rope. If you jiggle one part of the rope locally, the knot itself, the overall topological property, remains unchanged. The idea is that topological qubits would be intrinsically protected from local noise and errors, much more robust.
So they wouldn't decohere as easily.
That's the theory. Microsoft is investing very heavily in this topological approach, betting it might be the long-term key to stable, scalable quantum computing. But it's proven extremely difficult to actually create and control these topological states experimentally.
Okay, so decoherence is a huge problem. Keeping the quantum state alive. What other big hurdles are there, even if you manage the cooling?
Even if you keep them coherent for a bit longer, the error rates are still a monumental problem.
Errors in the calculations.
Exactly. Right now, even in the best systems, performing a single quantum operation like flipping a qubit or entangling two qubits has a relatively high chance of going wrong. The error rate per gate operation is often around, say, 1%, maybe a bit less in the very best cases, but still far too high.
1% doesn't sound that bad.
But think about running an algorithm that requires billions of operations. If each step has a 1% chance of error, your final answer is almost guaranteed to be complete garbage. The errors accumulate catastrophically.
Okay, yeah, that makes sense. What error rate do we actually need?
For practical, fault-tolerant quantum computing where you can trust the results of long, complex calculations, experts estimate we need to get those error rates down to maybe 0.0001% per operation, or even lower, maybe one error in a million or a billion operations.
That's a massive improvement needed. Orders and orders of magnitude.
It's an exceptionally difficult challenge, and it leads directly to the next huge hurdle: quantum error correction.
Fixing the errors as they happen.
Sort of. Because individual physical qubits are so error-prone, the idea is to use redundancy. You encode the information of one perfect logical qubit across many, many physical qubits.
How many?
Potentially thousands or even tens of thousands of physical qubits might be needed just to create one stable, reliable, logical qubit that you can actually compute with reliably.
Thousands of real qubits for one usable one.
Yes. These physical qubits would essentially constantly monitor each other, perform checks, and correct errors that occur in their neighbors, acting like a highly redundant self-healing system. Think of it like having 1,000 noisy, unreliable messengers who constantly cross-check each other to ensure the final message gets through correctly.
Wow, so that explains why we need so many qubits eventually.
Exactly. And it blows up the scalability challenge. Building a machine with just a few hundred physical qubits is already incredibly hard. Now imagine building one with millions or billions of physical qubits, all interconnected, all cooled to near absolute zero, all precisely controlled with lasers and microwaves, all managed flawlessly, just to get maybe a few thousand usable logical qubits.
It sounds almost impossibly complex from an engineering perspective.
It is a monumental engineering, scientific, and financial undertaking. You have to solve the decoherence problem, the error rate problem, the control problem, the connection problem, the measurement problem, all simultaneously and at massive scale.
Which explains why there isn't just one clear path forward, right? People are trying different approaches.
Precisely. It's clear there's no single right way to build a quantum computer yet. Kaku, in his book, describes this fascinating diversity of architectures that different groups are pursuing, each with its own pros and cons.
Like the superconducting ones you mentioned.
Right, superconducting loops or circuits. These are tiny loops of metal cooled way down so electricity flows with a zero resistance. That's the approach used by Google and IBM, currently leading in qubit numbers, but they require those massive dilution fridges.
Okay, what else?
Then you have trapped ions. Companies like IonQ are big on this. Here you trap individual charged atoms, ions, using electromagnetic fields, kind of like holding tiny marbles in invisible bowls. Then you use precisely targeted lasers to manipulate their quantum states.
Ions held by lasers. Sounds cool.
They tend to have very high qubit quality, long coherence times, and good connectivity, but scaling them up to large numbers of ions reliably can be tricky.
Okay, superconductors, trapped ions, what else?
There are photonic systems using particles of light, photons, as qubits. Companies like Xanadu in Canada are prominent here. Photons are nice because they don't interact much with the environment, so decoherence can be less of an issue, and they might operate at room temperature eventually. But generating, controlling, and detecting single photons reliably, and especially getting them to interact strongly for quantum gates, is really hard.
And the topological ones?
And then, yeah, the topological qubits we talked about, Microsoft's big bet, theoretically the most robust against errors, but still very much in the fundamental research stage. Hard to even demonstrate convincingly yet.
So different horses in the race, each with strengths and weaknesses.
Exactly. And because fully fault-tolerant machines are likely still quite a way off, Kaku really emphasizes the importance of hybrid quantum classical systems in the meantime.
Hybrid, using both kinds of computers together.
Yeah. The idea is you use a powerful classical computer to do the overall orchestration, the data input-output, the error management, basically all the complex control stuff. And then you hand off the specific, computationally brutal quantum parts of the problem to a smaller, specialized quantum processor, a QPU.
So the quantum chip does the heavy lifting it's good at, and the classical computer manages it.
Precisely. This lets researchers start exploring quantum algorithms and finding quantum advantage for specific subproblems today, using the noisy, intermediate-scale quantum NISQ devices we currently have, while the hardware technology for full-scale machines continues to mature. These hybrid approaches are probably essential for the next decade or more.
Okay, that makes sense. But with all this talk of mind-blowing potential, 10,000-year problem solved in seconds, it's really easy for the hype to get way ahead of the reality, isn't it?
Oh, absolutely. That's a crucial point.
How do we, listening to this, distinguish between genuine excitement about scientific progress and maybe exaggerated claims, or just understanding that practical uses might still be decades away?
That's a really important question, and it's something Kaku himself sort of implicitly addresses by, you know, acknowledging the criticisms that swirl around the field.
Right.
While his vision is definitely inspiring, and that's important for getting people interested,
Yeah, you need the visionaries.
you do. But some physicists and quantum computing experts argue that the book, and maybe the general public discourse around quantum, sometimes does oversimplify or even exaggerate the current capabilities.
In what way?
Well, they might point out that sometimes the really high error rates get downplayed, or the huge gap between a cool quantum supremacy demonstration, which, remember, solves a very specific, often deliberately contrived problem.
Right, not necessarily a useful problem yet.
Exactly. The gap between that and achieving real-world practical utility across a wide range of important applications is still significant. And maybe that gap isn't always fully communicated.
So is there anyone specific who's been critical?
A prominent and quite vocal critic is Scott Aronson. He's a distinguished quantum computing theorist currently at UT Austin. He's been very outspoken.
What does he say?
He actually went so far as to call Kaku's book the worst book about quantum computing, which is pretty harsh,
Wow.
primarily because he feels it perpetuates hype over substance. Aronson specifically takes issue with some of Kaku's broader, more sweeping claims, like the idea that quantum computers could solve every problem humanity faces.
Okay, yeah, that sounds like an overstatement.
Aronson stresses, quite rightly, that many of humanity's biggest problems are, social, political, logistical. They aren't necessarily computational problems that quantum computers can even address. And even for computational problems, he emphasizes, with real academic rigor, that quantum advantage is highly task-specific.
It's not a magic wand for everything.
Exactly. It's a specialist tool. It offers potentially exponential speedups for certain types of problems like factoring, simulation, certain optimization tasks. But for many other computational tasks, a classical computer might still be just as good, or even better. It's not a universal replacement.
So it's important to keep a balanced view. Appreciate the breakthroughs, but understand the limits and the challenges.
Precisely. While it's absolutely crucial to be inspired by the potential, and Kaku does a great job of that, it's equally important to maintain perspective. Understand that this is likely a long, hard road, and quantum computers won't solve all our problems. The challenge for us as informed listeners is to appreciate the genuine scientific excitement without getting swept away by, uncritical techno-optimism.
Okay, let's shift gears now. We've talked about the nuts and bolts, the hurdles, the hype. Let's dive into the really exciting stuff, the what-if scenarios. And yeah, it's still a big if, we can overcome these massive challenges. Kaku paints this incredibly vivid, almost cinematic picture of how quantum computers could fundamentally reshape our world. It goes back to that Feynman quote, doesn't it?
It absolutely does. Feynman's 1982 declaration really hits the nail on the head. Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical.
Simulate nature itself.
That's the core idea, and it's arguably the most direct, most profound application of this technology. Right now, our best classical supercomputers still struggle immensely to accurately model complex quantum phenomena. Think about the intricate dance of electrons in a chemical reaction, or how a protein folds itself into a complex shape.
They have to approximate.
Let's go approximate it using classical bits to try and represent inherently quantum behavior. It's like trying to describe a symphony using only Morse code. You lose most of the richness.
But quantum computers could do it directly.
Exactly. Because they are quantum systems, they could natively simulate nature at its most fundamental level, atoms, molecules, electrons. They could allow us to accurately model incredibly complex systems that classical computers can only give us rough sketches of.
And that capability, what could it unlock?
Kaku argues it could be the key to tackling some of humanity's most pressing global crises, designing revolutionary new materials atom by atom, understanding biological processes with pinpoint accuracy, developing truly sustainable energy solutions.
It's moving from just approximating reality to actually emulating it.
That's a great way to put it, emulating reality at its most fundamental level. And that potentially opens up a whole new universe of discovery and innovation.
Okay, let's get specific. One of the most direct impacts Kaku envisions is in our health and medicine. How could this change things for us personally?
The potential here is just staggering and, deeply personal. Take drug discovery. Right now, developing a new medicine is incredibly slow and expensive.
Years and billions of dollars, right?
Exactly. Typically 10 to 15 years, huge failure rates. A big reason is the sheer complexity of simulating how a potential drug molecule will interact with, say, a target protein in the body. There are something like 10 to the power of 50 possible interactions to consider, an impossibly huge number for classical computers.
So they have to use trial and error, mostly.
A lot of educated guessing and laborious lab work, but quantum computers could potentially simulate these interactions directly and accurately. Kaku suggests this could dramatically cut that development time, maybe even halve it.
You're getting life-saving drugs out in maybe 5 years instead of 15.
Imagine that, bringing new treatments for cancer, Alzheimer's, infectious diseases to market much, much faster. The impact on human suffering would be immense.
What about personalized medicine? Tailoring treatments to individuals.
That's another huge area. Quantum models could precisely map and understand the complex web of genetic mutations that drive a specific patient's cancer, for example. This could allow for highly individualized treatment plans.
So instead of standard chemo, something designed just for my cancer.
Picture this. Doctors could simulate how your specific tumor might grow and respond to different drugs or therapies virtually, using a quantum computer before they even give you a single dose. They could even optimize gene editing techniques like CRISPR-Cas9 at a quantum level to find the most effective way to target your faulty genes.
Testing treatments on a virtual twin first. That's incredible.
It really is. And then there's disease understanding at an even more fundamental level.
Take protein folding.
How proteins get their shapes. Right. When proteins misfold, it's implicated in devastating diseases like Alzheimer's, with those amyloid plaques, and Parkinson's, with alpha-synuclein clumps. Now, AI, like DeepMind's AlphaFold, has made amazing progress in predicting the final static structure of proteins.
Yeah, AlphaFold was a huge breakthrough.
It was. But quantum's potential superiority lies in dynamic simulations, understanding not just the final shape, but precisely how proteins move, wiggle, interact, and change over time. That dynamic behavior is often crucial for understanding how diseases actually progress and for designing drugs that can intervene effectively.
So quantum goes beyond the snapshot to the movie.
Exactly. And Kaku even pushes this into the realm of longevity, extending human lifespan.
Okay, now we're really into sci-fi territory.
Well, maybe. But he suggests that quantum models could finally let us unravel the incredibly complex, interconnected biological mechanisms of aging itself. Things like why telomeres shorten at the ends of chromosomes, or how mitochondrial damage accumulates in our cells over decades.
Understanding aging at the molecular level.
If we could truly simulate and understand those processes, Kaku argues, it could lead to therapies that don't just treat age-related diseases, but maybe slow down or even partially reverse the aging process itself. He talks about aiming for lifespans of 150 years or more.
150.
Building on current research, like studies on caloric restriction, and potentially designing entirely new anti-aging drugs conceived and tested within quantum simulations. It's ambitious, for sure, but the idea is that quantum could give us the insights needed to fundamentally redefine health and lifespan.
Wow. Okay, from drugs to longevity, what about the big global challenges? Climate change, feeding the planet.
These are absolutely central to Kaku's vision. He sees quantum computing as a potential game changer for sustainability. For environmental solutions, think about climate modeling.
Making better predictions.
Much better. Quantum computers could model Earth's complex climate system, atmospheric chemistry, ocean currents, ice sheet dynamics, with far greater precision than classical supercomputers can manage. This could lead to more accurate predictions, more effective mitigation strategies, and better ways to optimize things like carbon capture technologies.
What about weather forecasting?
Advanced, highly localized weather forecasting, too, predicting severe storms, floods, droughts with more lead time, helping communities prepare and adapt.
Okay, climate. What about feeding billions?
Here, Kaku talks about sparking a second green revolution, building on the first one from the mid-20th century. He brings up Fritz Haber again.
The fertilizer guy.
Right. His Haber-Bosch process for making ammonia fertilizer is crucial. It literally feeds billions. But it's incredibly energy-intensive, consuming maybe 2% of all global energy, and has a massive carbon footprint from burning natural gas.
So could quantum help make fertilizer more efficiently?
That's the hope. Certain bacteria do nitrogen fixation naturally, at room temperature, using complex enzymes. Quantum computers could simulate that natural process, potentially allowing us to design new catalysts that make ammonia efficiently without the huge energy cost and emissions.
That would be revolutionary.
Absolutely. And similarly, Simulating photosynthetic proteins help plants convert sunlight into energy with amazing efficiency.
You mentioned that earlier, nature being 90% efficient.
Right, while our best solar panels top out around 20–25%, if quantum simulations could help us design artificial photosynthetic systems or dramatically improve solar cell materials based on nature's tricks, it could transform renewable energy.
And crops themselves.
Yes, quantum modeling of plant genomes could help design genetically modified crops much more effectively. Crops with significantly higher yields, better drought or pest resistance, enhanced nutritional value, directly addressing global food security for a rapidly growing population. These aren't just small tweaks, they're potential paradigm shifts for planetary health.
It's amazing to think about the cascading effects. Better fertilizer, better solar power, better crops, all stemming from understanding molecules better. What about energy more broadly? Powering our world.
That's another huge area Kaku explores. In clean energy, think batteries. Quantum computers could simulate the complex chemistry inside lithium-ion batteries at the atomic level.
To make better batteries for EVs and grids.
Exactly. Designing batteries that charge faster, last longer, hold more energy, maybe use more abundant materials. That's critical for electrifying transport and storing renewable energy like wind and solar when the sun isn't shining or the wind isn't blowing.
What about the grid itself? Getting the power where it's needed.
Here, the dream is discovering new superconductors. Materials that conduct electricity with zero resistance, zero loss. Right now, most known superconductors only work at incredibly low temperatures, making them impractical for widespread use.
Like the quantum computers themselves.
Right. But if quantum simulations could help us discover or design materials that superconduct at or near room temperature, it would revolutionize power grids, enabling ultra-efficient transmission of electricity over long distances. It would also be crucial for things like fusion reactors and even future quantum computers.
And speaking of fusion.
Ah, yes, the ultimate clean energy source, fusion power. Mimicking the process that powers the sun, it's incredibly difficult because you have to contain plasma hotter than the sun's core.
Plasma physics sounds complicated.
Extremely. Simulating that complex plasma behavior is a massive computational challenge. Kaku argues quantum computers could dramatically accelerate progress here, helping scientists design better magnetic confinement systems or understand instabilities in the plasma. He points to the breakthrough at Lawrence Livermore National Lab in 2022.
Where they got more energy out than they put in. Net energy gain.
For the first time ever, yes, a huge milestone. Quantum computers could help us take the next crucial steps, optimizing reactor designs and bringing the dream of clean, virtually limitless fusion power much closer to reality.
Okay, this is all staggering. Medicine, climate, food, energy. What about the convergence with that other huge technology trend? AI.
Ah, the synergy between quantum and AI. That's where things get potentially exponential on top of exponential. Quantum AI is a field buzzing with possibilities.
How would quantum help AI?
Several ways. Quantum algorithms could potentially speed up parts of the AI training process, especially dealing with massive datasets or complex optimization problems that arise in deep learning. Imagine training vastly larger, more complex neural networks far faster than classical machines allow.
Leading to smarter AI.
Potentially, yes, quantum-enhanced AI systems could become exponentially more powerful and efficient for tasks like pattern recognition, drug discovery simulations, materials science, financial modeling, basically anywhere complex optimization or sampling is involved.
And could quantum computers help us understand the universe itself? The really big questions.
Kaku, being a cosmologist and string theorist himself, definitely explores this. Quantum computers could become essential tools for unlocking the universe's deepest secrets.
Like the Big Bang.
Modeling the very early universe, moments after the Big Bang, with far greater fidelity than ever before. Helping us understand the nature of dark matter and dark energy, the mysterious stuff that makes up about 95% of the universe, but which we can't directly see.
And the ultimate physics challenge. Unifying gravity and quantum mechanics.
That's the holy grail, quantum gravity. Trying to reconcile Einstein's theory of general relativity for gravity in large scales with quantum mechanics for small scales. They currently give contradictory answers in extreme situations, like black holes or the Big Bang. Quantum simulations might provide crucial insights, perhaps even help test predictions from frameworks like string theory.
So quantum computers could help us find the theory of everything.
It's a long shot, but they might provide the computational power needed to explore these incredibly complex mathematical landscapes in ways we simply can't today.
To wrap up this section, Kaku paints a picture of the future, right? A day in 2050.
He does. It's a captivating vision, a glimpse of how all these threads might weave together to subtly but profoundly transform daily life.
What does it look like?
Imagine waking up in a quantum-optimized smart city. Traffic flows seamlessly because quantum algorithms have predicted and routed everything perfectly. The energy grid, powered by fusion or quantum-enhanced renewables and managed by quantum AI, is perfectly stable. No blackouts.
Sounds nice.
Your breakfast might include food grown from crops designed using quantum simulations to be hyper-efficient and resilient. If you need medical attention, diagnosis isn't generic. It's hyper-personalized by quantum AI, analyzing your unique genomics and simulating treatment options just for you. Everything is powered by clean, sustainable energy, optimized minute by minute by quantum systems.
It sounds almost utopian.
It's definitely an optimistic vision, but it illustrates how quantum computing, working behind the scenes, could re-engineer solutions to many of the major global challenges we face today, making life fundamentally healthier, more sustainable, and maybe even unlocking deeper knowledge about our place in the cosmos. It's a future shaped by mastering the quantum realm.
Okay, we've spent a lot of time on the incredible promise, the almost utopian potential of quantum computing, revolutionizing medicine, energy, science. But like any truly powerful technology, there's got to be a flip side, right? A darker potential.
Absolutely. It's crucial we talk about the double-edged nature of this quibbit. Kaku definitely addresses this. There are significant risks and profound ethical questions we absolutely have to confront.
And maybe the most immediate, most talked about risk is our digital security. Everything we do online.
That's perhaps the most immediate and stark danger, yes. It's the one that keeps cybersecurity experts awake at night, and it stems directly from algorithms like Peter Shor's, the factoring algorithm we mentioned earlier.
The one that can break encryption.
Exactly. If or perhaps when someone builds a sufficiently large, stable, fault-tolerant quantum computer, Shor's algorithm could effectively break the encryption standards that currently protect almost everything online. We're talking about RSA encryption, the Diffie-Hellman key exchange.
Which are used for?
Pretty much everything sensitive. Global banking transactions, secure websites, HTTPS, VPNs, government communications, military secrets, corporate data, cryptocurrencies. The fundamental backbone of digital trust relies on the assumption that factoring large numbers is practically impossible for classical computers.
But not impossible for a quantum computer.
Not impossible at all, in theory. Shor's algorithm makes it exponentially faster. So connecting this to the bigger picture, it means that vast amounts of the world's currently encrypted data, financial records, classified documents, private messages could potentially become vulnerable to decryption by whoever gets that powerful quantum computer first.
So secrets we think are safe now might not be safe in the future.
That's the nightmare scenario. It's often called the harvest now, decrypt later threat. Adversaries, like intelligence agencies, could be vacuuming up encrypted data today, storing it, and just waiting until they have a quantum computer powerful enough to break the keys and read it all.
That's terrifying, actually. What's being done about it?
Thankfully, this threat is well recognized. And there's a massive global effort underway to develop and standardize post-quantum cryptography, PQC.
New kinds of encryption.
Exactly. New cryptographic algorithms based on different mathematical problems that are believed to be hard for both classical and quantum computers to solve. The National Institute of Standards and Technology, NIST in the U.S., has been leading a major international competition for several years now to select and standardize these PQC algorithms.
So we're racing to upgrade our locks before the quantum key arrives.
That's the race. It's a huge, complex transition that needs to happen across the entire global digital infrastructure. The fundamental insight here is that the very basis of trust in our digital world is being challenged at its core, and we have to proactively rebuild it for a quantum future starting now.
It really sounds like a digital arms race, but maybe with even higher stakes than we've ever faced before.
It has all the hallmarks of one. Nations aren't just competing for scientific prestige or economic advantage anymore. They're potentially vying for an unhackable communication advantage, or, conversely, the power to break everyone else's secrets.
Kaku calls it a quantum arms race.
He does, and the concern is very real. The nation or entity that achieves true, dominant quantum supremacy first, especially if they can build a large-scale, error-corrected machine capable of running Shor's algorithm, could gain an absolutely unparalleled strategic advantage.
What kind of advantage?
Imagine being able to decrypt essentially all classified communications from rival nations, or using quantum optimization to revolutionize military logistics, design unstoppable hypersonic missiles, or develop novel stealth technologies through quantum simulations. It could fundamentally shift the global balance of power overnight.
Creating huge power imbalances.
Significant imbalances. And we already see nations maneuvering strategically. We talked about China's Michio satellite for QKD.
The unhackable communication link.
Right. That's a clear step towards building a national communication network immune to quantum decryption, a defensive move, but also one that provides a significant intelligence advantage if others haven't secured their own communications yet. The insight is stark. Quantum computing isn't just a scientific tool. It's becoming a critical element of national security and geopolitical strategy.
Okay, so we have cybersecurity threat, the potential arms race. What about the broader impacts on society? Will quantum computing benefit everyone equally, or could it actually make things worse for some people? Deepen existing divides.
That's a critical set of ethical questions we absolutely must grapple with now while the technology is still developing, not after it's already entrenched. Kaku touches on this dual-use potential.
Meaning it can be used for good or bad.
Exactly. Quantum technology can drive incredible innovations in medicine, energy, materials. But the same power could be used for disruptive or dangerous purposes. Think about quantum-enhanced AI, for example.
We talk about smarter AI for science.
Right. But that same supercharged AI could potentially be used for developing highly sophisticated autonomous weapon systems with unprecedented speed and targeting capabilities, or for enabling mass surveillance on a scale we can't even imagine today. The potential for misuse is enormous.
And what about economically? Who gets access to this?
That's a huge concern regarding economic disruption and potentially widening inequalities. Building and operating these machines is incredibly expensive and requires highly specialized expertise. Access will likely be concentrated, at least initially, among major tech corporations, wealthy nations, and elite research institutions.
So the rich get richer, the powerful get more powerful.
There's a very real risk it could exacerbate existing economic divides, both between nations and within them. Less developed countries or smaller businesses could be left even further behind. And there's also the potential for significant job displacement.
How so?
As quantum computers and quantum-inspired algorithms become more capable, they might automate complex analysis, simulation, or optimization tasks currently performed by highly skilled humans in fields like finance, logistics, chemistry, or even software development. New jobs will undoubtedly be created, but the transition could be very disruptive for many.
So what's the answer? How do we manage these risks?
It underscores the urgent need for robust ethical frameworks and proactive governance. We need international cooperation, clear policies, public debate, and thoughtful regulation now. We need to consciously steer the development and deployment of quantum technology to ensure its immense benefits are shared broadly and equitably, while actively mitigating the risks from weaponization to economic disruption to algorithmic bias. We can't just let the technology run ahead and hope for the best.
We need to be intentional about building a responsible quantum future.
Exactly. And finally, Kaku, being the physicist he is, can't resist touching on the really deep philosophical implications, beyond the practical stuff.
Like the many worlds thing again.
Yeah, he discusses concepts like multiverses, the theoretical and highly speculative, possibility of using quantum effects, maybe combined with general relativity, to think about things like time travel via wormholes, even the deep mystery of consciousness and whether quantum mechanics plays a role in the brain.
Quantum consciousness? That sounds wild.
It's definitely out there on the fringes of science. But he provocatively suggests, for instance, that if quantum simulations ever did provide strong evidence for the many worlds interpretation, think about what that would mean. If every possibility branches into a new reality.
What does it mean for free will? Did I really choose to have coffee this morning, or did another version of me choose tea in a parallel universe?
Precisely. It would fundamentally challenge our intuitive notions of choice, causality, individual identity, the very nature of reality itself. These aren't just technical questions about building better computers. They force us to confront the deepest questions about what it means to exist in this strange quantum universe. #tag outro in.
Wow. What an incredible, truly mind-bending journey we've taken today. We dove deep into Michio Kaku's quantum supremacy, and honestly, we've covered so much ground. We started with the basics, that fundamental shift from classical bits to qubits, unraveling the weirdness of superposition and entanglement.
The spooky action.
The skooky action, exactly. We traced the fascinating history from ancient gears to Feynman's Damn It,
Right.
and explored those groundbreaking milestones. Sycamore, Jews hang proving quantum advantage is real.
Crossing that threshold.
But we also really dug into the tough stuff, the immense challenges of decoherence, those daunting error rates, the sheer engineering nightmare of scalability, and the need to navigate the hype carefully.
Keeping a balanced perspective is key.
Absolutely. But then we saw Kaku's vision for a future transformed revolutionary medicine, clean energy solving climate change, maybe even understanding the cosmos itself, while also confronting those critical ethical questions, the cybersecurity threats, the arms race fears, the societal impacts. I feel like if you've stuck with us, you now have a really solid, comprehensive grasp of this complex, often intimidating, but undeniably revolutionary field.
It's certainly a field that forces you to think differently. And as we wrap up, maybe a final thought for you, our listener, to mull over. What stands out to you most from this deep dive?
Yeah, what's the big takeaway?
Consider this. If quantum computers truly fulfill that Feynman dream, allowing us to simulate nature at its most fundamental level with unprecedented precision, pushing the boundaries from the intricacies of a single molecule all the way out to the birth of the universe, how might that fundamentally change our understanding, not just of technology, but of our own existence, our place within that universe?
It's beyond just solving problems faster.
Exactly. It's not just about faster drug discovery or better materials, as amazing as those would be. It's about potentially redefining what we even know to be real, revealing hidden layers of reality that quantum mechanics hints at. This deep dive explored the incredible potential and the very real, pressing challenges. The conversation about what it all means, though, that conversation has really just begun.